Hello everyone. So good morning. Today we discuss about many things. Okay. I'm planning to discuss 4 topics today. So it bit rush. I want to finish the queuing theory if it is possible. So we will discuss multi-server, queuing optimization, self-service queuing, and then the last one is queuing rule of thumb. Okay, so last meeting we have discussed about single server queuing, right? So do you have any question about last meeting, the single server queuing? I guess not.
I don't think so.
Okay, thank you. So today we'll discuss about, first thing is multi-server queuing. So this is an extension of single server queuing. Okay, so I will just review a little bit. This is the single server queuing, okay, in the top. So when the customer arrived, they join the waiting line, right? And then this is the customer that being served. Right? So let me get the pen. So this is the customer that being served. So we have only single server queuing. Next is another single server queuing. Oh, sorry. This is this is a single server queuing at the bottom here. Okay, but we have N server. So this is basically MM1. This kind is MM1, but multiplied by N. In this case, 3. Yeah. So when we talk about multi-server queuing, it's basically like this in the middle. So we have one waiting line, okay, and then we have multiple server. So in this case, M3, right? Because we have 3 server. Can you distinguish between MM1 and MMS? S is the number of server.
Yeah.
Okay, so this one is also MM1. Okay, so this one, the last part is the 3 times MM1. Okay, so I hope you understand the difference. Next, we have review. I just want to review the queuing system. So you know that in the queuing system we have input and output. The input are arrival rate and distribution, service rate and distribution, okay, configuration of the server, and then what is the waiting capacity, the population, and service discipline. Okay, the output we call it measurement of effectiveness or operating characteristics are as follows. So we have utilization factor, U, okay, represent the percentage of time that all servers are busy. We have P0, with this probability that there is no customer in the system. So what is this? The P0 represent the percentage of time that all servers are idle. Okay, so then we have the probability Pn that there are n customer in the system. Pw is the probability that the arriving customer has to wait for the service. And then FQT here is the distribution function of the waiting time, represent the probability that the customer will wait more than T unit of time. Okay, WQ, okay, and W is average time. This is called delay. Okay, average waiting time. WQ is average waiting time in line. W is average waiting time or the delay in line and being served. So this is average waiting time in the system. L and LQ both are the queue length. Okay, so the average number of customer in the waiting line for LQ, and then in the system, that means in the waiting line plus being served. Okay, so these are the output usually. So as the review again, we have Kendall notation of 3 letters, A, B, and K. Okay. A is the arrival distribution, B is the service time distribution, and K is the number of channels. So let's enter the MMS. Okay, so start with assumption, right? The assumption of MMS is that population is infinite, so it always come in, okay, based on random arrival, and the customer will join a single waiting line. I already show you in the drawing a short while ago, right? The arrival rate is following the Poisson distribution. The service discipline is FIFO, and then the customer must stay in the system until they are being served, okay, and finish. So, and then the waiting area is also unlimited, okay, and the service time is exponentially distribution, and all servers are assumed to be identical, okay, and the arrival rate is less than the system rate. And when the customer in front is, when the customer is being served is already completed, the customer informed is immediately served without walking time consideration. So look at this. These are the assumption of the basic MMS. So if you violate one of these assumptions, then you need to simulate, okay? Or you need to modify the formulation of MMS. Okay, so here is the formulation of MMS. So first, you compute what is called utilization factor, okay, which is based on 1/S multiplied by the rho. What is rho? Rho is mu over lambda, right? Or lambda over mu. So after you get the rho, okay, you can divide by the S. Okay, let's compare this with, I need to stop sharing. Let's compare this with MMS so that you will see MM1 so that you will see the difference. Okay, science, queuing theory, MM1. So if you look at the MM1 formulation, okay, mu is lambda per rho. Can you see this? Anyone?
Yeah.
Yeah.
We can.
Rho is lambda per mu, which is less than 1. Okay. And U is equal to rho. Can you see that? This is MM1. Now let's compare this with MMS. Okay. So in here you see mu is 1/S times rho. So the utilization factor is basically the same as rho, but it's the average of the rho, right? And remember, utilization factor must be less than 1. Why? Because this is random. If larger than 1, then the queue length and the waiting time will be infinite. Okay? Now, the computation of P0, which is probability of empty system, is the one that is complicated, right? So first you need to exponent the row, okay? And then you take the factorial of n. N is from 0 to s minus 1. S is the number of server. And then plus with the row multiplied by exponent to s, again divided by s factorial. And then you multiply by the s, multiply by the u, mu is the service time, right? Service rate. And then again divided by the s times u minus lambda. After you finish summation, all of these, then you take the 1 over that value. So, but you need to compute all of this if you want to compute by hand, okay? So, fortunately, I have made the program for you, right? So you don't need to compute by hand. So all you need to do is to go to this website and then you just input the arrival rate and the service rate and the number of server and then press the button calculate. You get everything. Is that okay? So basically this is just a calculator. Okay. So let's check. Can you calculate what if the service rate is 0.75 and the service rate is 1? Can you calculate the MOE? Can you go to that website there and then try to input the value? So what's the value? Anyone?
Wait, I'm trying it.
Okay.
Wait, sir.
Okay. So if you get the result, you can share with me. So if you have your arrival rate is 0.75 and service rate is 1. Anyone want to share?
I haven't finished. Maybe the others can do it.
All you need to do is to enter the website and then plug in 2 numbers there.
Where's the calculator again?
Check the slide.
Which slide? I'm looking through them all. But...
This one.
Is okay.
Okay.
Queuing.
Okay, for the number of server, we use 2 servers, right?
Server, yes. So it's your turn to share. Okay. So you get 0.75. Utilization factor is 37. So can you explain what's the meaning? Idle server is 45. So is this good or bad, Lillian?
I think it. Wait, wait.
Good for whom and bad for whom?
I think it's bad for the customer because like the queuing utilization is 37.5. Wait, am I wrong? I get mixed up. Wait.
Yes,
Wait.
it's the other way around, okay? So
Oh, okay.
when you said the utilization factor is 37.5, probability of idle server is 45, that is bad for the business,
Mm.
okay? The one that provide the service is having high costs in this case. Okay? The queue length, if for the customer, you look at the queue length and the delay, okay? For the
Really low.
you will see the probability of idle server, the queuing intensity, queuing utilization, right? So 37.5 meaning only 37% utilization. Okay, the almost half of the time the server are idle.
Mhm.
Okay, so in this case, one server is enough. Can you change that to one server? Okay, and calculate. See, it's already only 75, and 25% of idle server is good for business, right? So for this case, for this arrival rate and service rate, you only need single server. You don't need two server. That's the meaning. Based on numbers, then you can start to see, oh, how many server do I need, right? So the input is arrival rate and the service rate. And then the MOE is something that you need to interpret in order to find the number of server. Can you see that?
Yes.
Okay. So here, 75, that is good, right? So 75%.
Mhm.
So now depending on the service rate and arrival rate, then you start to think of the number of server. Okay, and then you guess the number of server, and then you calculate, and then you check the result, and then you do trial error in this case, right?
Mhm.
Okay. And any question? So far, so good. So
Sir,
yes, please.
if the standard unit is different, is that depend or affect the calculation, the result?
Yes. So you should not use a different unit. You should use the same unit. Okay. So for example, if the unit is customer per minute for the arrival rate, then for the mean service time or the service rate is also the same, customer per minute. Okay.
Okay, thank you.
Again, Karim?
Oh.
Okay, so this is what you need to do when you get the formula. Okay, you need to investigate what is the characteristic of that formula. So here is the plot that I plot using MATLAB in this case. Okay, between rho okay, versus L. L, what is this L? L is the queue length, right? And look at the graph. Can you interpret what is the meaning of this graph? Anyone?
Sir, what is the row?
Rho is lambda over mu.
Oh, okay.
So basically, you know that rho is lambda over mu. That means rho represent the utilization factor for MM1, right? So can you interpret what is the meaning of this graph? Anyone?
I try.
Okay, Mark.
If the row is high, the L also get higher.
And then
Then
why we have so
the
many line there?
I still don't know. Maybe because it's different cases.
Anyone else?
Maybe Abel can try.
Hmm.
Maybe it's the queue length for max utilization for each row.
No.
No.
Okay. Look at this way. Okay. The queue length for each row, okay, will become infinity when it reaches the number of server. So, for example, if the number of server is 1, here it is. This is the length. Okay. If the number of server is 2, this is the line. If the number of server is 3, this is the line. The number of server is 4, this is the line. Okay. What is the meaning? That meaning that for each row, okay, the number server will reach some certain type of, then the queue length will reach certain infinity. Can you see that? Means, okay, that means for each number of server, okay, there is a boundary. Okay? For each number of server, there is a boundary. You see, for server number 1, okay, if you have only one server, then this is the line, right? So this is the line for number of one server. If you have 2 server, this is the line. Then this is the boundary. If you have 3 server, this is the line, and this is the boundary. Can you see that? Okay. So for each number of server, okay, then there is certain kind of infinity. Okay. That means if your service if your service rate is too low, okay, and your arrival is too high, that is the equal to rho is higher than certain number, right? If your rho is, for example, 2.5, okay, if your rho is 2.5, how many server do you need? If your rho is 2.5, probably need 3 server, right? If your row is 2.8, you don't need 3 server, you need 4 server.
Mhm.
Okay, because if you have a 3 server, your value will be almost infinity. If you have a 3.8, for example, okay, you don't need 4 server, you probably need 5 server. So
Uh,
can you see that?
I'm a bit confused. So if row is 2.5, you need at least 4.
If you have a row 2.5, this is your line. I will draw the line. 2.5, you have this line, right?
Yeah.
So this one mean you have this point and this point. You see that? So this point represent that if you use only 3 server, okay, if you use only 3 server, your queue length will be this much. And then if you use 4 server, your queue length will be this much.
It's not being drawn on the screen, I think.
It is not being drawn in the screen. I will try to use different color. Can you see? This is the, can you
Oh
see
yeah.
blue? Okay. And can you see this blue in the bottom? So
Yes.
the intersection of the vertical line and the line that is going to infinity. Okay. The first on the top, okay, maybe I need to change the color so that you will see. So the one in, okay. Say your number is 2.8. 2.5 is not so clear. 2.8. So this is red. And then I change the color into green here. Okay, so about 2.8, right? Can you see
Yeah.
red and green? So if you use 3 server, okay,
Yeah,
rank is almost 20. Can you see that?
Okay.
Okay, if you use 4 server, your queue length is about 5. Right? And then if you use 5 server, the purple line, your queue length probably only 3. So between 5 and 3, you will say, okay, is the difference is too little, so I will just use 4 server in this case. Correct?
Wait.
Okay, another example. If you have your row is 5. Okay, this is 1, 2, 3, 4, 5, 6, 7. If your row is 5, how many server you will use?
6.
Yes, you will use 6, right? Because 5 is infinity, your queue length. Can you see that now? Right?
Okay. I
Okay.
think. Okay.
So if your row is 4.5, how many server you will use?
I think. Uh,
Again, you will use 6, right? Because if you use 5, you will have a 15 people
5.
waiting.
wait. If we use 5, we'll have.
About 15 people waiting.
Oh wait. Wait. So what does row actually mean here?
Rho is equal to lambda over mu.
So
You remember. So lambda is the mean of arrival rate. This one is the mean service time.
oh, so it's the service rate.
Yes, the service rate.
Okay.
Basically, this is the demand over supply. Okay.
Okay.
Okay. I hope you understand the meaning of this graph and the importance of this graph.
Okay.
Okay. Good. So let's go to the next. So for the same demand and the number of server, which one is better, single line or multiple line?
Multiple line.
Why?
If you have the same surface, multiple line, good, because you can reduce your queuing. But if single line, maybe for different part of surface, I think.
No. So
Mhm.
okay, you need to calculate. Okay. When you calculate, then you start to understand. Okay. If okay, I'll give you this practice number 2 as your homework. Is that okay?
Okay.
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 Okay. So you just put in the notepad or you can calculate using whatever you want. So this is your homework, practice number 2. So you need to increase the number of server from 1 to 10. And then you compare single line and multiple line. Is that okay? Okay. And then you plot between row and W, row and L. Okay. So I will put, and then you upload it to Moodle individual. Okay. So, and here is the result. Anyway, so if you look at the result, okay, single line versus multiple line. So single line is actually better in terms of what? Single line is better in terms of what?
Waiting time.
Yes, waiting time. Why?
Because they're not bound to one queue. A line is not bound to one queue. They can go to other servers.
Yes.
I mean, yeah, they can go to other
If you look at
servers.
the graph here, okay, the delay W here, the delay for single line is less than the multiple line. Can you see this? Can you see the chart? This chart. Can you see this chart?
Oh yeah.
Okay. So, and for in terms of queue length, okay, the multiple line is better from this chart.
Wait, can you repeat, Pincer?
Okay.
In terms of what?
Okay. Wait. I will share with you again. Can you see this?
Yeah.
I will help you when you analyze, okay, and then you plot, right? When you plot, you need to understand the meaning, correct? You don't just plot and then finish, right? So what's the meaning? You interpret this meaning. In this case, you need to find something that low, not high. Why? Because this is L. Oops. Okay. So L here is what? What is L and W?
L is queue length and W is waiting time.
Very good, Abel. So W is waiting time, is the delay. You want delay to be high or you want delay to be low?
Low.
Of course. So you want the queue length to be high or you want the queue length to be low?
Low.
Of course. Then you need to get the lower part, right? So look at this now. Which one is the lower? Between red and blue. In this graph of W versus rho, which one is lower, red or blue?
Blue.
Blue. What is the meaning of blue there?
So the single line have
Very good.
low delay time.
Very good. How about here in this graph? Between blue and red, which one is the lower?
Red.
Red. What is the meaning then?
So multiple line have lower queuing time.
Queuing length.
Oh
Not
yeah,
time.
queuing length.
Queuing time is the W, okay? Queuing length is the L. So you want to get lower, right? That means your answer earlier, oh, this one, okay, this one is better, is not necessarily true. Okay, better in terms of what? Okay, here the queue length is better. Okay, this one, the queue length is better. This one, the queue time, okay, the delay is better. Can you see that now? When you investigate, then you start to understand. If you don't investigate, oh, I get the formula, so what? Okay, you need to investigate more detail. Then you start to understand. Okay, so this is your homework. Okay, homework. Okay. Yeah. So for the same demand of service, multiple line is better in terms of queue length and single line is better in terms of waiting time. Okay. So now be careful, okay, with the assumption violation. So the previous cohort computation does not take into consideration of the walking distance. Okay. When the number of server is very high, for example, you have 20 servers, the walking distance between queue length and the server can be significant. Okay. So in this case, you can reduce to multiple line. Okay. So in practice 3, okay, to accommodate walking distance, additional 3 seconds to the service time per additional server from 1. So here we compute, okay, a single line is actually better than multiple line or not if we also include the walking time. Okay, so in here I plot it, then you can see that so can you interpret this? Which one is better?
Which graph that I have to plot?
Yeah, you point out which one is the one you want to interpret.
The first one, the queue length number of servers 2, the multiple line have better in queuing length, but
What's the same? Can you-
single line
I think this okay, I will put it
Lower.
A, B, C, D, E, F, okay? If you look at the A, okay, they are almost the same, isn't it? The two lines between red and blue are overlapping, correct? Okay.
yeah,
In chart D, the number of server is 5, okay? The multiple line is better in terms of queue length. Okay, the same with the in chart C, okay, the multiple line is better in terms of queue length. Now, in terms of delay, okay, in terms of the delay, whether the number of servers is 2, 5, and 25, the single line still better, isn't it? In terms of the delay. Look at the chart DEF. So the blue is always below. That means the single line is always better in terms of waiting time. Even if we compute with certain walking distance. Okay? But when the walking distance is rather slow, okay, so 25 seconds, that means that this walking distance is far. So that value is now reversed if you compare. You see? In terms of queue waiting time, okay, is no longer a single line is better. Can you see that? So if the number of servers is 25 in here, for example, there is an intersection in this point, right? And then there is an intersection in this point, okay? So there's an intersection that at certain point, if your walking distance is too far, multiple line is actually better. And what is that point? That is the intersection here. Okay, so row 3.5, and if the number of server is 25, row is about 24 probably, right? So now for the same demand and service and additional walking time, okay, so multiple line is still better in terms of queue length, but in terms of waiting time, okay, when the walking distance is low, then the single server is better. But when walking distance is high, then multiple line is actually better. And the behavior change at the number of server and the demand change. That's the conclusion of this analysis. Can you see that? So look, this is how I show you, okay, some kind of analysis come from the formula. So when you have the formula, you don't just take the formula as it is. You try to understand the meaning of the formula, you simulate. Okay? Okay, up to here, is there any question? If not, I will continue with the next topic, or you want to, still half hour, so you want to rest for it a little while, or you want to continue? Okay, let's continue then.
I will take a rest for a while.
Oh, you want to take a rest for a while? Okay, 5 minutes is okay?
Okay.
Okay, so
Enough.
now is 9:21, 9:26, come back, okay? Again, let's start again. Okay. So let's go to the next topic. The next slide you can download from Moodle, which is basic queuing optimization. Okay. So let's discuss the meaning of total cost here and the economic analysis of the queue. Okay. And then we discuss about queuing optimization and other type of optimization. So this is optional. Okay. So by the end of this lesson, you should be able to find the cost-effective queuing channel and cost-effective service rate, and you need to model your own queuing decision model. Okay, so A queuing system, okay, if you want to optimize, that is the system average cost will be equal to the service cost plus waiting cost. So when we said system cost, okay, that is the same as the demand and the supply cost. Okay, service cost is the supply cost, right? The waiting cost is the demand cost. Can you see that? So what is service cost in here? The service cost represents the expense of the owning, for example, renting or operating, maintaining the service facility. Okay, so in this case, we talk about the cost of the capital. What is the equipment? What is the cash register, the land, the building itself? Okay, and then all of this probably you need to compute also the depreciation cost. Okay, and you also discuss about operating costs. What is the rental fee? What is the labor fee? The material, the repair, the maintenance, the utilities, the gas, electricity, water, and so on, including the insurance and taxes. So all of these service costs, okay, is directly proportional to the level of service. For example, if you want to add more server, that means the service cost will increase proportionally. Why? Because you need to train more, you need to add more room, more service, more cash register, and so on. Right? So the service cost is directly proportional to the level of service. Next is the waiting cost. So the waiting cost occur when the customers stay in the queuing system. Okay, what is this? This is the cost of production loss when the employees wait for the tool, for example. The machine wait for the maintenance crew. So you cannot produce anything because your machine is broken, right? So there is opportunity loss of the present and future value of the profit based on customer dissatisfaction. They will go to your competitor to find the same service. Okay. The waiting cost is also representing fuel cost, environmental cost. For example, the aircraft, okay, waiting for the runway. Then they need to turn around in the air. Okay, every minute the amount of fuel discharge and the pollution is quite big. Okay, now the waiting cost will decrease when the level of service increase. So then we can start to think of economic analysis of the queue. Okay, again, economic analysis of the queue is actually based on subjective evaluation of the operating characteristic that you have. Okay, the more scientific way to use is to use the total cost model. So total cost depends on CW. What is this? CW is the unit waiting cost per unit time per customer multiplied by the L. L is the number of the queue length, basically, right? The number of average number of customers in the system. And plus the CS. What is CS? CS is the unit cost per additional server per unit time multiplied by the S. S is the number of server. Okay. Because L, okay, is equal to lambda times U. You remember the little formula last time we discussed. So then we can say that TC is actually equal to CW lambda times W, okay, plus CS times S. Okay, so if you plot, you will get something like this. Okay, So the blue line here represents the service cost, okay, with the CS times S. And the waiting cost is the pink line there, okay. If the number of server going up, the service costs increase proportionally, but the waiting costs decrease non-linearly, right? So then you add the two of them. That when you add the two of them, that become total cost. Okay. Of course, the total cost should be computed per time. So in this case, total cost per hour. Okay. Now, the optimization here is you will find the minimum total cost. Okay. In this case, if you find the minimum total cost, okay, the one in dot there in the dashed line, can you see? So that is the part that, okay, this is the optimum number of channel. Okay, so given the cost, the unit cost of service and the unit cost of waiting, okay, in this case CS and CW respectively, then you will be able to compute what is the number of channel that I need to put as the optimum value. So computationally, that means, okay, given the multi-server system, MMS, right? You know this is what is given. Lambda, you know, mu, you know, CW and CS. What is lambda again? Lambda is?
Arrival rate.
Okay, arrival rate, very good.
Arrival.
Rate, arrival rate, okay? So what is mu?
Service time.
Service rate. Okay, service time is 1 over mu, right? Service rate is mu. What is CW?
Cost of waiting.
Yes, unit cost of waiting. Okay. For example, if I wait for 1 hour, what is my cost? Okay, and what is CS?
Cost of serving.
Yes,
Oh.
cost of server. Okay, for unit cost of server. If you add one more server, how much? Okay, so the way to compute is basically you get you could compute as MMS. From S is 1, 2, 3, 4, 5, and so on. For each S, you will get L, isn't that? Right? Then you compute the TC. Okay. After that, you plot and then you find the minimum, something like this. So you got the idea?
Yeah.
Good. So if you want to compute by hand, go ahead, okay? But I have the calculator already built in, so all you need to do is to input the service rate, the arrival rate, unit cost of server, and unit cost of waiting. Then you can get the queuing optimization result. Say, for example, your arrival rate is 600, your service rate is 75, okay, people per hour. Then your unit cost of server is 100 and unit cost of waiting is 1. Then you need 9 number of server. Is this clear? Computationally, just plug in formula. Okay, plug in numbers into the formula or the calculator here. Is that okay? Okay.
Okay.
Practice. Okay, so you go to this website. Okay, and then you input this number. So what is the most economical number of channels? So your mu is 1. Okay. one customer per minute. Your lambda is 5, so every minute there is 5.75 customer coming in. Okay. So, say, for example, your cost is 50 per hour. Your opportunity cost of losing your customer is 15 per hour. Okay. So, how many servers do you need? Anyone want to share your screen?
I think I can.
Yes, please.
Here.
345.
So I changed it into hours.
Okay, okay.
So 345 is 5.75 times 60. And service rate is 1 times 60.
Correct.
And unit cost 50 and 15 or from the
Yes,
question.
yes, yes,
So yeah, the optimization result is 7.
yes. Very good, very good. Okay, very good, Abel.
Okay,
Very good.
okay.
So that is how you will. Okay, let me share again. Queuing optimization. So that is how you will compute. Okay, so yes, optimum number of server is 7. So in here I calculated using spreadsheet. Okay, this is the program. The program I make it long time after the spreadsheet. So okay, so there are many other ways to optimize the queue. Okay, so in principle, what you need to do is to find the conflicting measurement of the performance. Okay, so what is the performance? These are the performance. So LOS represent the level of service. If the level of service increase, okay, then this variable's value increase. And on the right hand side of the table here, these variables will decrease. Okay. Then you can match them. Okay. You see the conflicting value of the performance, then you start to find the optimization of your own. Okay, so I'll give you several examples. Okay, so for example here, instead of L and S, you can use mu and L, right? So the total cost here is depending on the service rate and the queue length. Of course, the cost, the unit cost will be representing the cost per unit, okay, in the service rate per unit time and the waiting cost per unit waiting time per customer. Okay, so the unit cost will follow depending on the unit. You can simply change the unit. Okay, this is another way. For example, here, if you use it for MM1, for example, okay, using this earlier formula, then you can calculate, okay, what is the optimum value. Okay, so the optimum value, you can take the first derivative and then equate it to 0. Then you will get the mu. Okay. Mu is equal to lambda plus square root of CW times lambda divided by C mu. So in this case, the service rate really depends on the arrival rate, and the optimal service rate is always greater than the arrival rate. Okay. So this is another example. Oh, what happened if I'm not using MMS? Okay. What happened if I'm using MM1N? What is the meaning of MM1N? That means you have arrival distribution random. Okay. You have surface rate is random, and you have only one channel or one server. What is N here? N represent the system capacity. That means your waiting line is limited up to N. Okay, your waiting line, say for example, if you have a room, your room is actually limited. Okay, what is the meaning of this limited? Meaning if the number of customers inside your waiting line is already full, okay, no other customer will go in. Okay. So in this case, you can use this formula for TC, which is for the total cost. Okay. The total cost here is depending on the mu, the service rate, depending on the L, the queue length, depending on the N, which is the system capacity or the total waiting line, and then depend on the PN. Okay, what is the probability that the system is full? Okay, so again, another example of computing the number of server based on MMS is to use this formula. Okay, so you want to find the number of servers so that two of the condition must be satisfied. Okay. One is the expected waiting time is smaller than certain threshold. Second, the percentage of idle time is below certain threshold. So you see these are conflicting. Okay. Then you can use this formula and you start to optimize based on this formula. So what is my point? Okay. The way you compute the optimal total cost, okay, it depends on how you model it. Okay. Of course, when we did not say anything, then use this traditional model, which is this one. Okay. So TC is CW times L plus CS times S. So if we did not say the model, just use this total cost model. Okay. So up to here, any question about the queuing optimization? Am I too fast or too slow? Give me your feedback.
From me, no.
So everything okay? Darin, can you follow?
I can follow, but I need to write what TC means like that.
TC means total cost in the system. There you can see.
Yeah. Later I will add in the line. Right.
So my suggestion is, if you feel that this is too fast for you, then you read before the class, okay? And if you need anything from me, if you have question, you can ask during the class or even personal question, okay? Okay then, so this is it for the
Yes, sir.
session. Next. What is next? Next is the ideal. Okay. So the ideal is called self-service queuing. So can you see this or not? Did I share it? Okay, so this is the next topic. Okay. So in self-service, what you need to understand is what the world said as self-service is actually not self-service. Okay. For example, self-service gas station is actually not self-service. Okay. In Indonesia, you have a prasmanan, okay, eating self-service, you eat by yourself. That is not actually self-service. Okay, so then what is self-service in terms of queuing in here? Okay, that is what I want to explain. And the formula I will just give you, and there is a calculator, then you just compute using the calculator. Okay, so self-service model, okay, have Kendall notation something like this, MM infinity. So the number of server is unlimited because customer is also the server. Okay, so but caution here, what is often as said as self-service actually do not fall under this category. Okay, so the following are not self-service. Okay, self-service gas station. So they said, okay, the customers serve themselves. The reality in the queuing point of view, the gas pump is the server. Okay, even if the customers serve themselves, this is not self-service. ATM. Oh, self-service banking, right? You can go to ATM and take the money by yourself, okay, without teller. Well, in terms of queuing point of view, this is not self-service because the ATM machine are the server. Okay, and if you say self-service restaurant, you take the customer will take the food by themselves. Again, in terms of queuing, this is not self-service because the table with the food are the server. Okay, then what is self-service? Okay, self-service is actually distributed server. Okay, self-service in terms of queuing system is basically distributed server. For example, you take a driver license test. Okay, the written part of the driver license test is a self-service because you take it in parallel. Okay, so one day I do a pedestrian experiments in one of the university that I taught before. Okay, so there is a filling form and we distribute the hat in the first time we have a channel. Okay, I put 2 students or 3 students to distribute the form and the hat, so they need to sign the consent form. But I saw the queuing is too long. Okay, so what I will do is I put them in the class and then distribute the form and the hat in the class. This is self-service. Why? Because now the students help themselves. I just put the form in front, then they distribute among themselves. Distributed system is a self-service. Okay. Another example, if you fill up the order form over the internet, okay, online service, this is basically self-service in terms of the queuing. So self-service in the queuing sense, yeah, that is the best queuing that we can model. Okay, so can you give other example of real self-service model? Anyone? Lilian? Can you give other examples of self-service model? Eugene, are you still there?
Yes, sir. Sorry, I just came back from toilet. I don't know
Oh.
what's wrong with my stomach. But yeah, I follow about the self-service with I'll think of an example.
Okay, Stephen, you have any examples?
What about all you can eat restaurant?
Hmm?
All you can eat restaurant.
All you can eat restaurant. Can you describe it?
Yeah, so basically they have like they have they will give a place for the meat and you just cook it and you cook it by yourself. Is it?
Cook it by yourself.
Yes.
So if it is a distributed, okay, for example, okay, in the self-service restaurant, in the setting that everyone is sitting on the table and they cook it by themselves, right? That is self-service.
Mhm.
That's correct. But if they need to wait to queue in the table to get their own food, that is not self-service. Okay. So if they get the water directly from the jar in the table, that is self-service. Okay. But if they need to get they need to queue to get the water from the dispenser, that is not self-service because the dispenser itself is the server.
Oh, okay.
Okay. So depending on the setting, okay. Can you give any other example, Michael?
Uh, hmm. Is it like Uniqlo? Is it considered as self-serving?
What is that?
Uniqlo is like a clothes shop. We use the waiter, not waiter. What is it? The employee is not helping you, right? You just try it yourself and then you just pay and then leave. Is it self-service? So the clothes is there, right? So the employee doesn't do anything. We just try it ourselves and then go home if we done.
Okay, so to take the clothes itself is self-service. Okay, but when
Okay.
okay, so when they pay, are they queuing in certain cashier?
Sorry.
Are they queuing in certain cashier when they pay for the?
Oh, yeah. Oh, not. Is yeah. The cashier is certain, right? In the position, in one position, right?
Right. So the cashier itself is not self-service, but in terms of picking up the, so this as a parallel is a serial queue. Okay, the first queue is pick up the product. In this case, the clothes, right? So in this case, self-serve. The second queue is in the cashier. That is not self-service, right?
Okay. Okay.
Okay. Abel, you want to say something?
What if when you want to grab your baggage from the conveyor belt in the airport, is that self-service?
No, the conveyor belt is the server,
Hmm.
right? The conveyor belt is the server, correct? The length of the conveyor belt is the server. The length of the conveyor belt is the server. Okay, so if the length of the conveyor belt is infinity, okay, then yes, it is self-service. Okay, if the length of the conveyor belt is very long, yes, it is self-service. Can you see that? Mn infinity, right?
Huh.
Okay. So having to know what is self-service and not, then you can start to get into the computation. Okay. So computation is rather simple. When you see the formula here. Okay. So in self-service system, okay, so the average waiting time in queue is 0. The average queue length is also 0. That means every customer that arrives will be served immediately, right? So in this case, the W is equal to 1 over mu. Why? Because immediately being served. So the waiting time in queue is 0. No queue at all. Okay? So then, of course, you can compute this in the calculator. Okay? And if you compare, okay, of course, for the same arrival rate and the same service rate, okay, the queue length of infinity will be the minimum. Okay? The delay also the minimum in this case. So this is like the ideal condition when you want to reduce the queue. So if you know the ideal condition, if you know the actual computation with this MMS, right? So then how are you going to use this knowledge to reduce the queue? Okay, then the knowledge is all you need to do is to create parallel server, okay, so that the parallel server will reach infinity. So in other words, try to do it online. Okay, try to do it using internet if it is information. So the MOE, the measurement of effectiveness of infinity, can be approximated using MMS if S is sufficiently high. However, of course, using the formula above, you can see that the infinity is much simpler, right? So, yeah, the MOEF infinity also show that the minimum boundary of the queue length and the delay can be achieved through the most efficient system of self-service model. Again, yeah, self-service model is the ideal, the best queuing system. Okay. So, is there any question? Up to here, is there any question? So if not,
No, sir.
yes. So if not, we will go to the next topic. Okay. So I will consider this topic as the last part of our queuing topic. Okay. So I'll go to Teknomo queuing rule of thumb. You can get the slide from the Moodle. Okay. So this is the last part, but this is probably also one of the most important part for you. Okay. I want to generalize what is queuing model in this case. Okay. So traditional queuing model represents the waiting line, right? So congestion is basically queuing, remember? Okay. And we are discussed about the math of queuing using MMS, okay? And this is the formula that you compute, okay? So, and we also discussed about the economic analysis of the queue. Again, this is the formula that you use, right? And of course, the math is look like a little bit complex, but actually it's not really complicated because the math is actually doable in spreadsheet. Okay, so I created the spreadsheet there. Now, why after today? So it's like 100 years after Erlang, okay, proposed the queuing theory in 1917. Okay, why we still have so many queue? Okay, so then I start to discuss about queuing rule of thumb. Okay, because basically people do not understand queuing. Okay, and the formula look like very complicated, right? And they need at least computer or an app in the phone to understand this. But now I want to try to make it simple. Okay, so what I will do is I created this formula, simple formula. Okay, S must be larger than N times R divided by T. What is S? S is the number of server. Okay, based on queuing optimization, anyway, you will get the number of server, right? N is the total number of customers. R here is the service time. Okay, not the service rate, it's the service time. And then T is the maximum time to finish the queue. Okay, so how do I get this formula? This formula, okay, I got from this picture. Okay, you remember we discussed about this morning. Okay, so this is the graph between the rho and the L. You remember that for each number of server, okay, you have certain boundary, okay, of the L. In this case, say we have that boundary is basically the utilization factor. Okay, what? Utilization factor is rho over S, must be less than 1, isn't it? But the rho is actually what? Lambda over mu, which is the arrival rate divided by the service rate. Now, what I try to do, what is actually lambda? Lambda is actually N over T. What is this? N is the number of customers in the system divided by how long we observe, isn't it? And then mu is 1 over R. What is R? Is the service time. So if we put this together, okay, then you get the queuing rule of thumb, right? You see? The rho is lambda over mu, which is equal to N R divided by T, okay? And the U is less than 1. So in that case, by simple algebra, you can see that S must be larger than NR over T, okay? So very simple. Using calculator, even using hand, you can calculate already. Okay. So I give you this example last time based on my project in New York, right? So now, can you try to compute the number of server in this case? In this example, okay, during morning peak hour, okay, between 6 o'clock to 7:15, okay, approximately 4,500 cars enter our campus. to drop the children to the grade school. Okay. Each drop point required approximately 60 seconds, okay, including maneuvering time and bring down the heavy luggage. And each car require about 10 meters to stop and maneuver. Okay, the length of the car is about 4 meters, but to maneuver, you need about 10 meters. Now, the question is, how long is the dropping line so that no children will be late for school? Do you get it or not? Can you try to compute? What is the server here?
The drop off line.
Yes, the drop-off line is the server. Okay. So this is clearly a favorite school, right? So the number of students in that school is about 4,500, and they all using car. So these are favorite school, expensive. They all using cars, and the earlier they come to the school is about 6 o'clock up to 7:15, because the 7:15 is probably already late. Okay. And they drop their children in the school. When they drop in the school, they require about 60 seconds to stop and let the children go out of the car. Right? So can you calculate what is the dropping line, the length of the dropping line? What do we have?
The N.
N is what? How many?
4,500.
Very good. And what else do we have?
Then the T.
A?
75 minutes.
Okay, 75 minutes. What is that? T, yeah? And then?
Yeah. The R.
And then R is?
1 minute.
60 seconds, yeah, 1 minute. Okay, very good. And then?
The S.
S is how many?
10 meter.
No.
Server is, I think.
The S is how many?
10 meter.
No.
NS.
S is N times R divided by T. Okay. S must be larger than N times R divided by T. So your N is 4,500. R is 1, right? And then T is 75. That means S, the number of servers, must be larger than 60, correct?
Yeah.
Okay. For each server is 10 meter. That means 60 times 10 meter. That means your length must be 600 meters at least. Correct?
Yeah.
So then you can create a meander, something like this. Okay. So instead of going straight like this, you can create a meander. So the queue length can be accommodated longer. So, do you get the point? Okay, another, okay. Another example. During the conference with 1,000 participants, lunch will be served. This is happening in Surabaya in a hotel, okay? So participants will queue to get their food, their own food from two sides of table. Each person I check using stopwatch, require about 45 seconds on average to get his or her own food. How many tables of the same food are needed actually to let the eating time to be finished in 30 minutes? Okay, lunch time in conference is limited time, right? So say 30 minutes. It's a big conference, international conference with 1,000 participants, okay? And they serve only 2 sides of the tables. So question is, how many tables do you need?
So N is 1000, right?
N is 1,000, very good.
R is 45 seconds.
R is 45.
T is 30 minutes.
Yes, from there can you calculate the S?
And 2S. So
Oh, divided by 2.
yeah, divided by 2.
So how many?
12.5. So,
You
so
need
15.
Correct. Should be larger than, okay? So then you need 13 tables, okay? Unfortunately, okay, this is happening in Surabaya, in Shangri-La actually, okay? So unfortunately, the organizer did not understand queuing theory. Say they serve only 4 tables. So then the queue length was super high, and we cannot finish in 1 hour. Okay. Do you get it? Okay. Oh, registration is online. So this is like the offline registration. Okay. So this is another example. A grade school of 10,000 students. Oh, how many students in Petra? Anyone knows?
6,000, if I'm not mistaken.
Huh?
6,000,
6,000.
or maybe I have to find it in the respective team.
Okay. So anyway, this
That
school
there.
have 10,000 students. Okay. And then they set a certain days of registration, right? So from 17 to 19 or something like that. So they register, and then there's a tuition fee payment. So basically a serial server to get the registration form, and then check all the delay payment, pay at the cashier, and then get the certificate of payment, and then the parent can go home. Okay. So 1 working days is from 8 to 5 minus 1 hour lunch break. Each parent need about 36 seconds only to be served by all the serial server. Very fast, right, actually? So now my question is, how many days are needed to register all the students? Assuming 1 parent, 1 student. So what do we have?
The N,
N is,
10,000 students,
okay.
10,000 students.
Okay, what else do we have?
And then the T,
Hmm?
T,
T is
time,
what? Time?
17 minus 8, so 9 hour.
No, 8 hours. Minus 1 hour lunch break, so 8 hours.
For 8 hours.
This is not the T. The T
And then
is one.
the R
R is what?
is 36 seconds.
Yes. So actually, what is the
Unit.
what is the you need to convert the unit, okay, to be equal. So
Yeah.
the T is what is the T in this case?
8 times 60, 480 minutes.
No. The T is something that you need to find. How many
Like that.
needed to register all the students. In this case, you want to know the T.
So T is X.
T is X, you need to know. Okay. So then S, what is S in this case?
1.
Exactly. Why? Abel, why? Excellent. How do you know that S is 1?
I just assumed it was 1 because
Why?
there's only one server, right?
Yes, it's only one server. Why? Your intuition is very good, but you need to reason. Why? Okay. Okay. When you have a serial server, okay, when you have a serial server, for example, you go from registration form and then check the delay and then pay the cashier. After that, go to payment. It's a serial server, right? One serial server is basically one server. Regardless how many servers there, is basically one server. This is the common mistake in queuing, okay? They thought they provide server, it's actually serial server, then it's actually only one server. When you want to solve the queuing theory, solve the queuing based on the queuing theory, what you need to do is to create parallel server, not to create serial server. You got it? Okay. All these people that serve, okay, with certain specialization is actually creating a system of serial server. Do you understand when I say?
So it's basically one line, right?
Correct. Okay. When I said serial server is something like this. Right? So this is basically one single server of multiple services. So always, if you want to break the queue, okay, never create a serial server. Always create parallel server. That is the lesson. Do you understand? Okay. When you start to create parallel server, oh, this person is only for checking. This person is only cashier. This person is only for giving the certificate. Then you create a serial server. When you create a serial server, your service, your actual server is only one. Regardless how many people you put there. Now you understand?
Yes.
Okay. So, can you solve this problem? How many days are needed? So S is 1. Okay. Then you need to know the T. Can you calculate the T? Anyone?
It's 12.5 again, which means it's 13.
Yeah. So it's 13 days. Okay. Simply because even though to serve one person is only 36 seconds, okay, you need 13 days. This is ridiculous. Why? Because the actual server is only one. Okay? And this is happening all the time. Why? Simply because they don't understand what is queuing theory. They thought, oh, I put a lot of server, but they created a serial server instead of parallel server. Can you see how stupid if the person who doesn't understand queuing theory, right? The waste of resources a lot. Okay? Okay, now this is another example. A church with 500 members, okay, in each service. After the worship service, there is a clearance of 30 minutes before the members of the next service can enter. The worship room has 2 doors. Each doors have 2 meter width. So each pedestrian can pass the door with a 0.5 meter width. The crowd speed is 0.1 meter per second. The question is the 30-minute clearance enough to let all 500 members out? Yes or no? What do we have here? And what is the server in this case?
We have the N, 500 members.
N is 500 members.
The T
T
is
is
30 minutes.
30 minutes, very good.
30 minutes.
Yes.
And
Number of
the
server.
S is 2.
Yeah, the door is the server, okay? So then
Yeah.
2 doors, meaning you have only 2 servers. Okay, the server is not
Yeah.
human, okay? So in this case, the door is the server. So the door has 2 meter width. Okay. If you know the width, okay, and the crowd, then you can calculate more. Okay, can you calculate in this case? Easy, right? Come on.
Uh, uh, so wait, the S is only 2.
This is only 2.
So, but the pedestrians can go through, 4 pedestrians can go through the door at the same time. Wait, and because there's 2 doors, 8 could go in at the same time.
Mm-hmm.
Wait,
And the speed is 0.1 meter per second. So can you finish it in 30 minutes? In fact, you can already estimate how many minutes if you have 2 doors. Then of course the suggestion is to add more doors if not enough, right? Or to add the more clearance time rather than 30 minutes. Probably you increase it to 45 and so on, right? The policy is clear. Can you calculate?
oh, so the S becomes 8 then? Oh,
Huh? Yes. So the S now become 8 pedestrian. Okay.
okay, I see.
Okay. So the speed 0.1 pedestrian per second, that's become the R. Okay. So then you calculate in here the T. Okay. The T is basically 625 seconds. So that's about 11 minutes. That means less than 30 minutes clearance, right? So 30 minutes clearance is more than enough. See? Simple or not?
Simple.
Somewhat.
Somewhat. So this is practical or not? My question to you. Okay.
Practical.
Yes. Look. You can change the door of the church into a door of a movie. You can change it into the door of a stadium, right? Correct or not? Instead of church, you can change the facility into a stadium. For example, soccer game. How many? right? How many watcher, right? And then is the door enough or not? You can calculate that, isn't it? Is the clearance enough or not? How long is the queue length? Okay, so okay, practice. Okay, use queuing rule of thumb. Okay, to compare which one is better. 6 person doing specialized tasks in series. Okay, average time is 30 seconds per customer, or they perform as parallel server. Okay, that means the average time increased to 1.5 minutes per customer because they are not specialized. Can you understand the problem? So you have a 6 person. Okay. The question is, should I specialize in certain tasks? Or I'm doing only payment. I'm doing only cashier. Or I'm only doing the stock. Okay. Or they perform as parallel server, meaning they are not specialized, right? That means their average service time, okay, is now become 1.5 minutes per customer. Instead of 30 seconds per customer, now increased to 1.5 minutes per customer. So which one is better, parallel or series in this case?
If without calculation, I think the parallel is good
Why?
because you can do all the tasks by one people in only 1.5 minutes. If the serial, if the parallel server, maybe you have the series server, you have to do one task only 30 minutes, and maybe if there more than 6 or 7, you make the queuing more longer, I think.
So we calculate, okay? So you calculate. So T should be larger than NR over S, isn't it? So in T1, you calculate as N is not known, right? So then you just put it in the value, okay? So T1 is 90 over 6. The R is 90. 90 is parallel server, in this case, 1.5 minutes, right? Over 6. So 15N. The T2 is 30 over 1 because only one server, right? So that 30N. So the specialization is not necessarily good, you know. Okay. So specialization is only good if the service time can be decreased as much as the number of serial servers. Okay. So the lesson here is try to create parallel server as much as possible. Okay. In queuing, the lesson is not about the computation, because the computation you can compute using calculator, right? But the idea is to create parallel server as much as possible. You get it? And of course, if you want to know that, you need to identify which one is the server in this system. Okay, is it the door? Is it the table? Is it the person? Is it the machine? Okay. You need to identify which one is the server. Okay. So is it the length of the dropping point? Is it the, oh, in the airport, okay? The actual server is actually the length of the meeting point. Okay. So in that case, if you say meeting point, point is just 1 point, that is wrong. See, a lot of system, okay, is making it wrong just because of the name. It should be meeting line rather than meeting point, isn't it? Because if you put meeting point, then the server is only one. Okay, so you check which one is the server and then try to create parallel server as much as possible. Is that clear? Okay, and remember, these are not self-service, so by putting self-service, you basically create parallel server. Okay, so queuing can be reduced, can be eliminated. Okay, and remember, I try to generalize what is queuing. Okay, queuing is the process where the people, material, or information need to wait at a certain time to get the service. Okay, so queuing system should be based on the purpose. What is the purpose that I need to queue? Okay, is it transfer of information, or is it transfer of material, or is it transfer of people, or is it transfer of things between the customers and the server? Okay, so this is just to summarize. Okay, in traditional point of view, queuing is just waiting line. If we generalize, then queuing become a process where the people, material, information need to wait to get the service. Okay, and this generalization is profound. Why? Because now you can think queuing in terms of demand and supply. You can generalize to think of everything as a queue. Okay, document waiting in the office between one department to the others is a queuing system. Okay, so remember, customers represent the users, okay, or the entities that seeking the service, while the server are anyone or anything that providing the service. Okay, and this is repeat from the beginning. Okay, in the traditional queuing system, okay, the customer arrive in the queuing system, and then they need to wait, okay? And then when they are being served, okay, there is a transfer of information between the customer and the server, okay? And then the server need to input certain data, for example, and then the server need to do the order processing, and the real things is the last, which is the transfer of material or the information from the server to the customers. So if you look at this, okay, many of these are actually information that you can simply put into the online system or using internet, right? So information transform can be transformed, information transfer can be transformed into the internet. While the physical things like material or the people transfer, of course, cannot be transformed. Okay. Now the critical question is, does the system need to transfer the physical things or not? Okay. In the past, for example, oh, I need to transfer the money. The money is paper or coins. Okay. The question is, do we really think that money is paper or coin? Or actually just numbers? Okay, so then the question is this information or is this physical? Right? So, look, the first step in queuing analysis is question why. Why do we queue? Is this queue necessary or not? Right? Second question is, start to separate the information from the material. Okay. Then you identify if it is really necessary and this is material queuing, okay, then you start to identify the server. And then you start to brainstorm the solution, okay? The solution are four things, okay? One is to increase the number of parallel server. Second, to increase the service time. So usually through training, okay, or through better machine, right? Third is to reduce the number of customers, okay? You get appointment, for example. And next is to increase the time period to serve the team. Okay. So up to here, any question? Can you think that logistics system, okay, or good distribution system from the factory to distributor to large retailer to small merchant and to customer, can you think this as a queuing system? Hello?
We need to discuss it first, sir.
So logistics system, okay, which is from factory to distributor to retailer to small merchant, finally to customers. Can you think this as a queuing system?
Yes.
Yes.
Okay, describe it.
The goods may have to
Yes.
wait from the factory to the distributor, and then
Yes,
wait to the large retailer, and then
right,
wait again until it got to the customer.
right. So then if this is a queuing system, then you can start to see, okay, is this a parallel system or is this a serial system?
Serial system.
No, in fact, it's a tree diagram, right? So this is actually a parallel system. Why? How many factory? Probably
A
one.
lot.
No, say paper. Okay. Say you have a paper factory. In one factory, how many distributor?
Many distributor,
Many distributor. For one distributor, how many retailer?
many retailer,
Many retailer. For one retailer, how many small merchant?
many smaller merchant.
Exactly. So then this is basically very efficient system of distributing. So what happens if we cut short from the factory directly to the customer?
There will be queuing.
Long queue in the factory,
Yeah.
correct? Okay.
Yeah.
So then you start to think, okay, oh, the whole trading system, okay, is actually very efficient from the queuing point of view, isn't it? People will start to, if I think you hear the news, oh, we need to cut short because the middleman is the adding cost, isn't it? The middle trader is adding cost to the system. If we cut short the factory directly to customer, we may have a better system. But if you do that, what will happen is you will have a long queue in the factory. Okay? It's not
Okay.
really better. Of course, you need to compute, okay? The parameter, the variables will be different. So not necessarily better. In fact, if you do directly from the factory to the customers, then you will create a kind of distribution system inside the factory. Rather than external, now you make it internal. Isn't it? Okay, so the middleman in the logistics system is not necessarily bad. Yes, they add costs, but that cost is probably necessary, okay, to distribute. Okay, can you see that or not?
Yes.
Okay, so basically this is hierarchical system. Okay, so when you cut short from factory directly to the customer, you have a flat parallel server. So then the question is, how many servers do you need, right? So you need to compute that using queuing theory. You can use. Okay. Okay, so tell me, what things you think as material, but actually it is information?
Money,
Money. Okay, what else?
time,
Time. Time is not information already.
and then worker,
Worker is material or information?
information.
It depends, right? So construction worker, is it material or information?
Information. Material.
Explain to me. Why,
If,
why is it information?
because we need to teach them how to make the bridge.
Hmm?
We need to teach them how to build the bridge, and then they can do as what we told to them.
Okay. So workers at this point, okay, because of your lack of technology,
Mhm.
is basically still material,
Hmm.
right? But you are right that worker is actually information,
Mhm.
because when the robot take over, right?
Mhm.
Oh, do you know 3D printer,
Yeah.
right? So basically, using machine, you can create a parallel server, okay, using robotic, right?
Mhm.
In that case, the worker skill is no longer necessary because what we need is the information, their knowledge, which is
Mhm.
through the machine, right?
Yeah.
Okay, what else? Very good.
Maybe the other can help.
Yeah. So what is you think as material, but actually it is information? Eugene? Abel? Lillian? Michael?
Customer.
Customer? What? Customer is information or material?
I think it is information, just like when we download Grab or Uber, the company have information about who wants to be delivered and who wants to deliver them.
Okay. Mhm. So if the customer is information,
I think so.
okay. So your ID card is information or material? Your KTP,
It's information.
information.
It contains information.
Yes. So then do you actually need to queue to get that information?
For NIK and stuff, yeah, I think so. But for the rest, like tempat tinggal, name and stuff, no.
So many of government services are basically provide information,
Yeah.
right? So do you really necessary to go to government office to get that information? Is your trip to the government office necessary or not?
I think no.
No, because this is information. So you start to contact them using email or using chat, right?
Yes.
Is it information or material?
Can you reply?
Teaching, learning in the school, is it information or material?
Information.
Information. Then online teaching is better than offline, actually, isn't it?
Yes. Yes.
Yes,
I agree.
you agree. Okay. Of course, meeting is different. Meeting offline is necessary to get better feeling. But at the same time, in terms of the material, okay, of the course, it is information.
Mm.
So something that information can be put into online through the internet, right? So your job to be, is it information or material?
Information.
Information. Your house is information or material?
Material.
Material, yes. Oh, when you kiss your girlfriend or your boyfriend, is it material or information?
Real.
What?
Kissing is information or material?
Material.
Material.
Rodney is only asking
Uh,
question about boyfriend and girlfriend, yeah.
the first one information, the second one material. I think. more than that material.
How about sex? Is this information or material?
Yeah, the first one is information. The second and the is material, right?
Right. Well, the feeling is information. Okay. The act can be material. Okay. But the sensory activities is basically information. That means that information can be transferred through technology. That means in the future technology, okay, kissing can be remote, sex can be remote. Can you imagine that?
What?
So
What?
only the
What?
feeling that can be remote, right?
Meaning in the future technology, not now, okay? I'm just
Okay.
in the future technology, if you think this is actually information, that means it can be remote, can be used online. So all you need is a device to connect with the thing.
Okay.
Okay, I try to make you open mind, okay, that right now it is material. The same is your worker. Worker is right now probably material, okay? But in the future, probably information. Because basically it is information. Can you start to see? Okay.
Yes.
Okay. So by identifying, okay, material from information, you may be able to transfer the material Q into information Q, right? Hence, to eliminate the need of the material Q itself. Okay. So work from home, okay, online learning, online meeting will reduce the traffic congestion, right? So the key is actually information. So in that case, hotel registration to get the key to the room is unnecessary because basically they are numbers. Okay, so again, what will be the impact of 3D printer and robotic toward the material world? Okay, your house right now is material. Okay, but what if you can simply design and use the robot to build a house for you? Right?
Right.
Then it is becoming partially information, you see. Okay, so what is the future technology will change the way of we live, right? So if you want to predict the future, okay, what you will be thinking is, what is information? What is material? Okay, what will be the impact of the internet speed? Okay? If it is very high and the internet cost is very small, what will be the future job? What will be the future of the school? What will be the future of congestion? What will be the impact to the family relationship? Okay, based on queuing theory only, then you can start to think about these kind of things. Any opinion?
I think I want to give opinion.
Okay, go.
I think if everything become cheap and then you get all information fast, you have to learn how to serve other people. Like what they need, we have to give it. Yeah, maybe we have to change our orientation, like serving for God, not for human, and then change how we serve, like in totally. Yeah, maybe we have to serve in the rest of our life. I think that.
Great. Any other opinion about the queuing theory?
I think when we do with the parallel system, I think it can make all things done in the faster way. But when we do it in the serial, we have to wait for a long time. But it depends. All depends in where you live, which country, and the other stuff. And I think the worker now is the material, but in the future there will be information.
Okay.
I think that I can give to you.
Yeah, thank you.
You're welcome.
So, okay, what did you learn so far in this class? Especially, this is the finishing. This is the end of the queuing theory. Okay. What did you learn so far? I want to.
When you want to learn something, you have to have commitment and you have to consistent in learning. It takes time, but all can make you a better person.
Okay, try to do that, Darin. Okay, I want to see your presentation next.
Yeah.
Okay.
Okay, I will.
Yeah.
Try.
Eugene, are you there? Are you calling me, sir?
Yes.
Yes. So I think what I found most interesting was actually the one that we just learned. Like
really?
where actually I when you give the question about the church, and I think yeah, that will be useful for me to make money in future. I
Oh,
mean,
really?
like I don't know what kind of job that I will apply, but I
Mhm.
think that is one of the realistic knowledge, and I think even though not much, one or two people will need that knowledge, and when that time come in handy, that knowledge will be useful to me.
Mm.
That's why I want to, yeah, I want to understand that really well because
Mhm.
I get the feeling that I will need it in the future, even
Oh,
though I
cool.
don't know what exactly, what kind of a situation that I will face against in the future.
Right. So, so the material of game theory and queuing theory, is it useful for you?
I think so
Mm.
because it's
Queuing
not
theory is
something
very useful.
theoretical like we learn about uh, molarization in chemistry, and if you mix the solution and the solution, what is the color of the final solution, like that. That's the stuff that we learn in high school, and I don't think that is applicable in real life unless you're a scientist. But this
Mhm.
one, I think, yeah, this is the real life. This is real world, like what we need to solve, like something that we think, ya gitu-gitu aja. But yeah,
Mm.
actually, if you can find a solution, it will it will be money for you.
Mm. Abel, you have some opinion?
Yeah, I have the same opinion that like fine.
What
Finally,
did you learn so far? Yeah.
when I look at game theory, I find it a little bit harder to apply to myself. I can't imagine myself making a matrix for a decision like that. But for queuing theory, I can clearly see that it's incredibly beneficial.
Mhm.
So yeah,
So queuing
that's what I think.
here.
And it motivates me more to learn about it because I know it's immediately practical and
Mhm, mhm. Lillian, you want to say your opinion?
Oh, so basically, I don't really understand about queuing at first, but now I'm starting to understand what is queue. Like there's tons of different type of queue that I just know.
Mhm.
So yeah,
How about comparing game theory and decision making last time, right? And queuing theory, which one you understand better?
I think the queuing theory.
Queuing
I
theory is
prefer
better.
queuing theory though, rather than game theory.
Yeah.
Really? Okay.
Because like I don't feel like
Sorry.
I don't feel any like relation or connection with game theory, but about this queuing theory, like the time, the end, and stuff. Yeah, I think it's yeah, I can grasp it better
Okay.
comparing to game theory about probability and stuff.
Oh no. So because the next lesson will be a Markov chain and Max and IFN, probably a little bit higher compared to this. I hope you're okay.
a little bit higher.
I hope so.
I mean, in terms of the mathematics. I will try to deliver it in an easy way. Michael, you have any opinion?
Me? Uh, um, uh,
Come on,
no,
Michael.
maybe.
You only answer question about boyfriend and girlfriend. Come on, Michael.
And but if you ask me if I understand or not, I think yeah, yeah, a little bit. I think just a little bit, but yeah, 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 yeah. I cannot say anymore. Okay.
Which one you understand better? And what did you learn?
Oh, for the game theory and the queuing, right?
Yeah, and decision making.
Uh, right now I think it's game theory because we just have had exam
Okay.
because I yeah, but so I cannot say that I understand queuing theory better. But in the future, maybe maybe I will try to understand it more.
Okay. So in that case, the exam will help you to understand.
It I must understand for the
Okay.
exam. I must understand.
So you have homework from game theory, okay? I will post it in Moodle. Okay, so
Okay.
make it. Eileen, you have some opinion?
Actually, I find today's material very interesting because it is very applicable to day-to-day life.
Hmm.
It I think it's practical to use also.
Okay, which one you have a better impression?
Since I start in the middle of the class in the decision making, I cannot say that it's my most comfortable, but it's actually okay with me in the queuing theory and game theory.
Stephen,
Yes, sir.
you have some opinion about this class and
I think I'm agree with Rodney, sir. I'm agree with Rodney. Midterm make me more understand, I think.
oh, the exam. Okay, in that case, we will have quiz next week, okay?
What?
Um, when you want to have a quiz about the theory? Is it next week?
Guys?
Next week.
Guys, hello guys.
Why not? Sure.
It's just 5-minute quiz like last time. Probably only 2 or 3 questions, multiple choice. But it's just to force you to learn, and then you will know better. Is that okay? So when do you want to have a quiz about it?
Okay.
Next
Oh, guys.
week. Let me check the date. Next week is a holiday or not?
I think no.
No. When is the Lebaran?
12 until 14. Oh, wait. 12 until 14.
12 until 14.
14.
So next week we have class, 18 we have class. Is that correct?
Yeah. Maybe wait. I don't know the Petra schedule.
And I want to ask you one thing. Suppose the material is not finished, okay? The one that I posted in Moodle, because we have only a few more classes, right? Suppose if it is not finished, do you want to have a makeup class?
Long as the time is available, it's convenient, yeah, why not?
Okay, then what date and what time?
How about Saturday?
We have to discuss it first.
Yes,
Uh,
discuss it among yourself. And then
really?
tell me.
Saturday? You want?
I'm fine any day, except
Really good. Because
Saturday,
we are
what time?
free all day at Saturday.
Okay. Okay, Saturday what time? Just in case only.
I think before the evening, I think 8:30, like usual.
8:30 in the morning.
Yes.
Okay. Okay, so 8:30 to 11:30.
Okay.
Okay, just in case. So I will announce if we have a makeup class. Okay. So far it's okay. I will try to speed up if we have time. Next week we discuss Markov chain, right? Is that correct? In the Moodle.
In the Moodle, yes.
Yes.
The order is after this Markov chain.
Markov chain. So can you read it first before the class?
Yeah, okay.
This is not so easy. Okay. So Markov chain is not so easy, but I hope you can read first. And I want to do it in one time if possible, in 3 hours. So a little bit fast. Yes.
The 11 May, I think it's written in the calendar academic is a holiday, national holiday.
Oh, next week is holiday.
Yeah, on the 11.
Oh.
11, 12, 13, 14, 15, 16.
Oh, no,
So
I
1
think
week.
the last time we got an update, it like so the Lebaran starts from 12 until 15.
Oh, really? Oh, I don't know. I just checked the calendar academic.
11 is holiday.
On the calendar academic, but Lily said there's an update, so I don't know.
Email.
Okay, you
really?
decide. You decide. I don't really mind. So you decide whether we will have class next week or not.
I think we should.
Yeah, I
think
think it's fine if I have a class.
Right. So we will have class next week. Okay.
Mhm.
Okay. Good. So we have class next week, 11, and then so I will give you homework. So in that case, I will put a quiz next week. Is it okay? All queuing theory in the beginning until today. Only queuing theory in the test.
Okay.
You just read before that. Okay. And Markov chain, you read first. Okay. This is not so easy. Did you have a background in programming and linear algebra?
Not so strong background, yeah. Not so strong.
But you know how to multiply, you know how to transpose, you know how to take inverse. Is that correct?
The
Should
matrix?
be able to. Oh,
Yeah.
should be.
The matrix, right?
Matrix, yes.
Yeah.
Can.
Yeah, I can. Yeah, little. Can lah. I won't be so confident to say like, yes, we master it. No.
Yeah, okay. Then check the slide and try to do it on your own if you can. Then we can start to discuss about it. Basically, the difficulty in Markov chain is there are so many terminology that you need to memorize. So then please read first, okay? Okay, so shall we start with the Markov chain now?
Okay.
Yes or no?
It's okay. We have time.
We have
The
time, right?
class.
Okay, I will start then.
Okay.
Where is the Markov?
Or how about the others?
Markov chain is in statistics. Okay, Markov chain. Yes. Okay, let's start then. So first, before Markov chain, I want to discuss about stochastic process. Okay, and then I will discuss about general Markov chain and then the finite Markov chain. Okay. So, okay. All of you have learned statistics, right? You know what is the meaning of random, right? So, random process or the stochastic process is basically a family of model, okay, on what is called dynamic random state. What does dynamic mean? Dynamic means time dependence, okay? Depends on time, okay? So time domain can be discrete, can be continuous. The time can be discrete, meaning 1, 2, 3, 4, 5, or continuous. Continuous means real numbers in the time. So what is random? Okay, dynamic random state. What is random? Random means having or being elements or the events definitely have certain probability occurrence. Okay. Next is the state. What is state? State is the internal property of the system, okay, that together with the input of the system will reveal the output. So, I will try to draw. Okay. So, if you think of system, okay, have input and output, okay, inside the system, the interconnection between, say, this one in the node inside the system is called state. Can you understand the meaning of state here? Okay, the state are the internal properties of the system inside the system. Okay, when you get the input, it will reveal the output. Okay, the state are the internal properties of the system, meaning the node of the system. Now, the system can, the state can be discrete and continuous, and then can be represented as random variable x. Okay. Next is definition of what is called stochastic process. Okay. So stochastic process is a random function that represents trajectories of the state over time. Okay, I will show you in Excel so that you will understand this. We'll open Excel. Okay, and I will create what is called random walk. Can you see my screen or no?
Yes, we can.
Okay, so I have time here. Okay, then I will have what is called random walk, xt. So I will put the time is discrete, so I will add +1. Okay, and then in the beginning I will put 100. Okay, then I will say this one plus, okay, there is a random walk. That means I will have a normal distribution, inverse norm, norm inverse, norm inverse. Okay, or maybe norm inverse, this one, norm inverse. Okay, so in the norm inverse, you need to have a probability and the mean and standard deviation. Okay, so the probability I will put it as random. Okay, the mean I will put it here, and the standard deviation I will put it here. Okay, so there. So this is the mean and the standard deviation. So the mean is 0, the standard deviation is 1. Okay, now I have the formula of random walk. Okay, then what I will do is just copy it down, right? will copy this down. Oh, I know why. Because this one must be. This one must be with the. Okay. There. Okay, this one also, I will put it here. Then I will plot, okay? Then I will plot. So let's plot it. Insert XY, plot it as this. Can you see this?
Sir, can you show me the formula?
Okay, I will show you the formula. Anyway, this one is recorded, so I hope you can.
Oh, okay.
So the formula is simple. Okay, norm inverse random of the mean and the standard deviation. Okay, if you don't like the string, I will name it. In here, I name it mean, right? And then in here, I name it standard deviation, STD, STD. And then I change this into mean and standard deviation, comma STD. So I name it into variables, okay? There. Copy this, and then going down, Control V. Isn't it? No, it doesn't work. Oh, there. Okay, so the formula will be norm inverse of the random of the mean and standard deviation. And now you have a random walk here. Okay, so this is basically a random walk. And what we have, can you see that? So if I put press F9, function 9, so I have different values. Can you see that?
Graphic.
Yeah, the graphic. The charts will be different. Right? Can you see it or not?
Yeah, right.
Right. So every time I press F9, the graphic will be changing. Okay. So let's come back to the slide. So the actual XT, what is XT in here? Okay, is a random function that represents trajectory of the states over time. So this is the XT, the one in Excel that a while ago. Every time I press, this is a trajectory, isn't it? From 100 up to here. This is trajectory. Every time I press F9, I will have another values. One of these values, okay, one of the trajectories, okay, so represent the random function, one realization. Okay. Now in this slide, what I show you is, look, if you put so many, okay, random walk over time, okay, then the chart is something like that. Okay. Now, we can also create an experiment. Okay. So you need to distinguish the term state and stages. Okay. State with T and states with T. Can you see the difference? Can you see the difference between state and stages? Okay. So we can describe a stochastic process as a simple experiment with a finite number of possible outcomes within the state, which take place in stages. Okay. Example, we toss a die first. And then if the outcome of are certain numbers, such as 4 and 6, then we toss the first coin. And if the outcome of coin is head, then we toss the second coin. If the outcome is tail, then toss a die again, and so on. Can you see the stages and the states? Can you imagine this? So first you toss a die, right? So that's the first stage, right? And then if the outcome are a certain number, like 4 and 6, okay, then you toss the first coin. If the outcome of the die is not 4, if not 6, what happened? Then it stopped. Okay. If the outcome is 4 or 6, then you toss the first coin. If the outcome of the coin, this is the second state. Now, the second state is to toss the first coin. If the outcome of the first coin is head, then you toss the second coin. Now, this is the third stage. Okay. So the first is to toss a die, right? And then you toss a coin. Okay, the first coin. And then you toss another coin. And then if the outcome is correct, you come back to tossing a die. So you create a network. Can you imagine that? Okay. Now the outcome of one state depends on the outcome of the previous states. Okay. The probability of each possible outcome at particular states is known when the outcome of all previous stages are known. Okay. So Markov chains, okay, that stages are in Markov chain, that stages are called time. Okay. If the stages is space, you will have another field. It's called Markov random field. We will not discuss in this class. Okay. So now the finite possible outcomes like the head, the tail, 1 to 6 of the die are called state. Can you distinguish between stages and states? Okay. Now, the variable to locate where we are in the experiment is called random variables. Okay, up to here, any question? Do you get the meaning of stochastic process? Do you get the meaning of Markov chain in this case?
Can you explain a little bit?
Okay. So, say you toss a coin or you toss a die. Okay. This represents some experiment, some random experiment, isn't it? When every time you toss a coin, you taste a die, it's now when we say stochastic process, okay, first you do tossing a die, then you do tossing a coin. Okay, now depending on the outcome of that coin, then you do something else. Then you create a kind of network. Okay, the first time you do tossing die, next you do tossing a coin. So the time in here, okay, are the stages. Okay. The outcomes of the coins is head or tail. Okay, that represent the states. My question: can you distinguish stages and the states? Can you understand what is stochastic process?
So if stages is the process and the outcome is what you get with your experiment, the learning
Outcome is the
outcome.
state. Okay. The outcome is called the state. Okay. Now, what is definition of Markov chain? Markov chain is basically stochastic process. Now, we discussed not the stochastic process earlier, right? With a special property, okay, stochastic process with the special property that all information about the future state containing in the current state. Okay. So conditional future state distribution depends only in the present state only. And it is independent of the past. So Markov chain is basically telling that, look, my decision today, okay, yes, it depends on the past, but my decision today is basically based on what is today's situation. Okay. So, or the previous situation. So in Markov chains, okay, you basically create what is called sequence of variables. Okay, I will come back to the example in Excel here. Can you see this?
Yes.
Okay. Once x1, okay, x1 depend on x0, isn't it?
Yeah.
X2 depend on x1.
Yeah.
Okay, that means the decision to go up or go down is just
Sir,
one previous value.
I think I need to leave now.
Okay.
I need to pick my mother in.
Okay. Okay.
Sorry, sir.
Okay.
Thank you.
I think we need to stop also the class, right? It's already 11:30.
Yeah, it's okay.
Okay.
Yeah.
Yeah. Okay. Thank you very much then. We will see you next week.
I think my group,
Okay.
which was,
Okay.
I think my group is supposed to discuss something after this.
Yes, you want to discuss something after this? So go ahead.
Okay.
Okay. So the others can dismiss, please.
You guys wanna go?
Okay. So who is your members, Abel?
So it was supposed to be Eugene and Rodney, but
Sorry, Eugene left already. Sorry.
Eugene
Yes.
had to go. So
Hmm.
basically, we have a brand new idea.
Okay,
Yeah.
go ahead.
So remember when we met earlier in Saturday or something? I said, what is the optimal? We wanted to find the optimal way to board an airplane. So right
Yes.
now we decided, why not apply the same principle to parking lots, right? Because usually the biggest problem when you go to a parking lot is finding a parking space, right?
Okay.
So wouldn't it be nice if once you go through the gate, like at the gate, you
Mhm.
get assigned a spot so that you don't have to find it, right?
Okay.
So we want to find a way. Let's say we have a continuous amount of cars waiting to go
Okay.
in. We want to
Mhm.
save time, right? So we want to find the optimal way to position these cars in order so that they and us waste as little time as possible.
Okay.
So I looked up on this theory, and it looks like it'll use like a Markov chain Monte Carlo optimization algorithm or something.
CMC.
Yeah.
Okay.
So I'm thinking, I was asking if, like, I wanted to ask if this is an acceptable idea.
Oh, your idea is always acceptable. I'm telling you. The question is, can you do it or not?
Will we learn about this
MCMC,
MCMC?
no.
Oh, we won't?
We won't.
Oh,
This is more advanced than Markov chain.
well then.
Yes.
But
I wrote some chapter about this, but if you want, you go ahead, no problem.
okay, so
You need to know how to
we already
program.
found we already found the data for it. So
Yes. You need to know how to program to do MCMC. This is basically MCMC is you randomize the system, okay, and then you want to find the states. To find the states, you randomize the system, and then you gradually reduce the threshold, okay, and finally it will find the optimal value. So how do you relate the parking lot with the MCMC anyway?
So because at the start we wanted to do the airplane version, I looked up a bunch of ways to do it, and it says the airplane version uses MCMC. So I assumed the parking spot would also use MCMC.
Not necessarily. MCMC is just one of the optimization. You can use later on we will discuss about max N, maximum entropy, right?
Okay.
You
Will
can
that?
use that.
Oh, we
Yes.
can use that for the parking spot?
Yes, sure. Oh, very, very powerful. The max N is very powerful.
Oh, okay.
Excel.
So we will be able to do it, right?
Yes. Instead of MCMC, you try to use max N.
Okay, I see.
Okay? And this is also very powerful inside your the scope of the class, and you can use Excel rather than MCMC, because in MCMC you cannot use Excel yet. Yes, you can, but you need to do macro.
I see.
Right? In max N you can use Excel using Solver.
Okay.
Okay.
So it will count as a semester project then, right?
Yes, if you finish, yes, of course. Why not?
Okay.
Okay.
Okay. Thank you.
Thank you.
okay, thank you, sir.
Thank you.
Darin, you want to talk to me? Darin,
Yeah,
what do you
yes,
want to
sir.
say?
I think I will change the project
Into
water system, maybe
water, what?
water. Like people need fresh water, right?
Okay.
Then they have to get a better quality of water.
Mhm. And then
Then how if we try to make the system of the water, like use the organic stuff to get a better quality? Or that's hard for me.
I don't know. I don't really know what is your strength and your weakness. Okay. And what project you want to do is, can you show me something that you want and show me that you already have certain progress first? Okay. Because if you just say
Because
this opinion today, tomorrow I have another opinion, then keep changing your opinion. This is already more than half semester. It seems like it will be very difficult for you to finish. Just make it simple. So among this that we learn in the class, which one you think is easier for you? Is it queuing theory, game theory?
queuing theory,
Queuing theory. Okay, then can you apply queuing theory in certain scenario?
Maybe when we want to enter the church,
Okay, can you really get, so what church you want to do?
GKI Diponegoro.
Okay, so you measure the door length and how many people there usually? How many seats?
We have to calculate it.
No, you
I
just
have
measure. Yeah, you need to go there, you need to measure. Is that okay?
I think if before Corona, before COVID, it can take about 1,000 people maybe.
Okay, so you go there, check the number of the real seat and the number of people there, how many services, get all the data that you need, okay? And then calculate using queuing theory. That's it. Is it simple?
I think that's simple.
Okay, then doable, right?
Yeah.
Then you said, then you give suggestion, oh, this is enough, or it can be optimized like this, optimized like that. Can you?
I hope.
Okay. And tell your group mate, okay?
Yeah.
Okay. So rather than you keep changing your opinion, so stick on something that you already know and try to use this knowledge.
Okay.
Okay?
Thank you for your sharing.
Yes, thank you. I will end now, okay?
God bless you, sir.
Yeah, see you next week.